The focus of this video is going to be on key critical properties of different measurements. Okay, so the first um, set of definitions that we want to kind of talk about is accuracy, uncertainty, and precision. Okay, so something that accuracy is defined as how close a measured value is to the actual value of the process or property that we're trying to measure. Right? We can estimate how, and then precision that deals with how small the difference is between when multiple measurements are taken of the same value. Okay, both accuracy of our measurements and our precision contribute to uncertainty, which is basically how a quantifiable amount of the variable that we're trying to measure, how close we think we are to it, or how confident we think we are, our measurement is to that exact variable. So a lot of times, maybe if you were measuring, maybe let's say the temperature of something, you could say that we're confidently think that we're within plus or minus maybe a degree Celsius of the actual value of that object. Okay. Um, So the next thing is repeatability. So example would be if you weighed yourself 5 times over the course of a minute, all right, you collected data, this following data set, all right, and you can say that the repeatability of the scale or the process of weighing yourself was about a pound based off of this data, because you basically varied between 149 to 151 pounds. Okay. Reproducibility would be if you had two different scales. Maybe you have an analog scale and a digital scale. On the uh, um, on the dial scale, you have the range that we just said between 149 and 151 pounds. While on the digital scale, you said you were between 151.0 to 150.9, I'm sorry, to 151.5. So you have a smaller range on the digital scale, only 0.6 pounds, but your average is higher. It seems like on the digital scale, it thinks you're 151 pounds, while on the dial scale, it thinks you're 150 pounds. Okay. So the idea behind reproducibility is basically the closeness of output readings for the same input with varying data collection conditions, such as a change in environment, okay? Or a change of instrument, like was shown here, a difference in observer, so who's looking at the dial scale, for example, etc. Okay. The last one is resolution. All right, resolution is the smallest change in an input to a sensor that causes an observable change in output. Okay, so if we look at this dial thermometer, for example, you can see that between each tick mark represents about 2 degrees Fahrenheit. So you could say maybe if you can interpret between the individual tick marks uh, on the thermometer, you can maybe say you can measure about a degree Celsius. That would be the resolution of that. While the scale on the right, you can see this is like a weight scale, and you can see it gives the last decimal place would be the resolution. So around uh, 0.1 pounds would be the resolution of that scale. Okay. Um, For the linearity and sensitivity, all right, we can basically say that we can define the sensitivity of a device as basically the relationship between the measured quantity, which is typically our input, okay, and the output reading of our device, okay? So we can oftentimes, this is a linear relationship, okay? So the sensitivity we can think as the slope of this line, okay? Linearity is basically the relationship between the measured quantity and the output reading of our device and how close that relationship is to a linear line. So ideally, we have a perfectly linear relationship between the two, and we can basically use this equation to basically solve for the sensor output very accurately. Okay. Okay. And then here are some additional properties of the of different devices: zero drift, sensitivity drift. Okay, so zero drift is basically says often is that typically the slope between our input, in this case of pressure, and then our output of our device, all right, it follows a linear relationship. But sometimes we get this displacement or this difference between what we think should happen and what actually happens. And it's not that the slope has changed, but just where there's just this offset value, right? So oftentimes we can adjust a scale electronically by basically measuring the pressure at a known pressure, measuring the output of the scale, and then subtracting that value, and then we can just measure the change in pressure to get the correct value. Okay. Sensitivity drift, on the other hand, is when our slope of our relationship between our input of our sensor and our output changes. Okay, so in that case, we would need to adjust that relationship in order to get an accurate reading. Okay, so oftentimes we can have both zero drift and sensitivity drift. And the only realistic way that we can count to get rid of this, all right, is if we can, in order to determine these different things, the sensitivity and the offset, a lot of times what we have to do is a process called calibration, where we apply a set of known values to our instrument, and then we monitor the output and recalculate both the slope of the line as well as any offset that we might have between the input and output of our system. Okay. All right. So what I would like you to do, all right, is please close this video, all right, and well, wait a second, don't close it yet, but put away your notebook, all right. Just try to open a blank sheet of paper with a pen and a pencil. Okay? And I ask you to just try to recall and write down as best as you can the following definitions, okay? In your own words. It's okay if you write something down and then it's wrong, all right? But do your best to try to write down the definitions of these words and see, after you're done, you can rewatch this video and see how close, or maybe the past, watch this video and see how close you were to these actual values. All right? Thank you very much for watching, and excited to see you all in class soon later this week.